NanoHub U, online instruction.
Hello and welcome back to NanoHub U's Introduction to Bioelectricity. I'm Professor Pedro Irathoki at Purdue University, and this is our fifth and final lecture of the Practicum series. In this series, what we're trying to do is take the theoretical knowledge that you're acquiring in the remainder of the course and apply it to actually building a device which takes bioelectric signals and uses them to do something useful. So far, what we've done in the Practicum in the 7.1 is you built an amplifier. In 7.2, you took the amplified signal and filtered it to get rid of the low frequency and the high frequency noise with the bandpass filter. In 7.3, you digitized that data. In 7.4, you took that digitized data and you added that circuit onto the Raspberry Pi, streamed it out wirelessly, received it wirelessly with your laptop, and you are now using your laptop to wirelessly record EMG signals from the body. The Raspberry Pi itself might be plugged into your laptop, but if it is, you're only using that for power. Alternatively, you can use a power adapter and plug it into the wall, and then it looks wireless in addition to being wireless. But with a Raspberry Pi as your Wi-Fi router, you can actually get your internet access through it, but more importantly, you can transmit these bioelectrical signals. Now what we're going to do is we're going to do something useful with the bioelectric signals that you've transmitted. And this is a project portion of the course. So there's the homework portion, which you've now completed, and then there are two project sections of the course. One is the modeling of the Hodgkin-Huxley equation that you're doing in the remainder of the course, and particularly in lecture 6.5. And here, it's the hands-on practicum portion of the project. And what you're going to do is you're going to control a prosthesis using a bioelectric signal. So in the fifth week of lectures, we talked about applications of bioelectricity, and one of them was targeted muscle reinnervation and prosthesis control. Here, we're going to go back to that, except now you're going to build a prosthesis controller that an amputee could use to control a prosthetic limb, or that you can use to control something else. Something entirely different. Your imagination is the limit, but I'm actually going to leave it fairly open at the end of the semester and give you the opportunity to step outside of the confines of this course and come up with something creative for extra credit. We'll get to that in a little bit. All right, so bioelectric prosthesis control. What you're going to do is you're going to use an EMG _BMI.py file that we've also provided for you at the beginning of this course. And you're going to see that that file, what it does is it has a bunch of resources. It's important that the resources directory be in the same subdirectory as the EMG _BMI file is on your laptop. And when you run that file, it'll pop up a window, and on that window will be this graphic. We are engineers. We are not artists, so the graphic is limited by our artistic talent. But anyway, it's a drawing that we made of an arm holding a weight in kilograms because we're engineers and we don't use pounds. And so when you use your EMG incoming data stream, you're going to need to find a way to take this graphic and taking the electrical activity you recorded with the analog front end with the amplifier that you filtered, that you digitized, and then you transmitted with the Raspberry Pi, you're going to be able to make that arm flex on your screen. So the fourth homework that you did in the last part of the practicum was to collect the EMG data from a series of muscles, the bicep, the forearm, the quadriceps, and then to quantitatively compare them. What did you find when you did that? Now, you had the option of using others. You even could have used the electrooculogram, the EOG, to record eye movements. You could record facial twitches, whichever you like. But you will have seen a variety of different signal amplitudes, and you will have seen a variety of different noise levels. Compare them. Which ones were the best signals? Which ones were the strongest signals? Based on that, you'll be able to do the homework for the project part. The homework is that based on the EMG data that you calculated from those three muscle groups, and then you measure the signal amplitude and the noise, what should the gain have been? So pick one muscle that you're going to be using for this project, and then tell me what should the gain be so that you use all of the dynamic range of your A to D? What should the high pass and low pass cutoffs be so that you sandwich in the signal of interest and cut out everything that is not in the signal of interest? So what is that bandwidth that those signals lie in? Can you remove everything else? And if you remove everything else, what would the new R and C values be for the analog front end to give you the gain and the high and low pass cutoffs that you would want to have? Once you've calculated those R and C values, I want you to go back into your circuit and replace whatever R and C values are in there with the necessary R and C values to get what you calculated. So I want to see the work for those calculations. I want to see the values that they should be, and then I want to see before and after photographs of your circuit showing me that you've replaced the values, and then you should be able to then hook it right back up to the same muscle, and you should get much better performance, a better signal-to-noise ratio, a better quality signal coming out of your A to D in streaming. Once you do that, you assemble everything up again, you measure again from those 3 muscle groups, and I want you to compare the previous EMGs that you got from those 3 muscle groups to the new EMGs you're getting from those 3 muscle groups. And that'll make the point that a custom bioelectric front end is always going to be better than one that's of one size fits all. And it'll also walk you through and away from how we began, which is basically spoon feeding you values and telling you to build it, and to becoming an engineer, a designer, somebody who looks at a problem, understands the data they're going to be processing, and is able to design a circuit to acquire the signals in the highest quality resolution. And then you're going to be able to start using them. So with the BMI project, you're going to do the installation. You're going to install Piglet. Then you're going to run EMG_BMI .py, and you're going to then modify the Python code. So we gave you a Python code file. You're going to go into that Python code file, and you're going to find a section in that code that says your code goes here. And your code is going to take the incoming data stream, and instead of plotting it as we did in plot.acquire in the last practicum portion, what you're going to do is you're going to process it. And then once you've processed it, you're going to give the output, not to a plotter, you're going to give the output to the controller for the arm, so that the arm that is straight as the default position, when you flex your muscle, the arm will also flex. So the two will follow each other. And if you do this right and you're using the bicep, then as you move your arm, the one on the screen will move. And that will show you that you have, in fact, built an algorithm that will allow BMI control, brain-machine interface control. So your algorithm should reference the literature in BMI. I don't want you to just go out and write whatever algorithm, some threshold detector. I want you to actually go out and find a paper that talks about brain-machine interfaces and some way of doing signal detection, and then implement some version of it. It can be as simple as you want it to be. I just want to know that you found a paper on brain-machine interfaces, that you read it, and that you implemented some version of it. So reference that paper that you cited, the paper that you read, implement that published detection algorithm, or make one that's better that references that one as a starting point, and then use it to control the virtual prosthesis you see here. If you want to go a step further, you can do the extra credit portion of this course. And this is entirely optional, and it's extra credit, but if you do it and you do it well, it can be worth up to 5% additional extra credit on the overall semester. And what I would like to see you do here, if you're interested in the extra credit portion, is to move away from the virtual arm on your computer screen towards controlling a real-world device. So when we talked about targeted muscle reinnervation, I showed you some of the data from our collaboration with the Rehabilitation Institute of Chicago, where we're using myoelectric data to control the prosthetic arm. So here you have a student wired up with an early prototype of our device, and then when she closes her hand, the robotic hand closes. When she opens her hand, the robotic hand opens. When she closes it, it closes. When she opens it, it opens. So she can open and close her hand, and the robotic arm follows her. Just like the virtual prosthesis on the computer screen will work when you're done with the practicum. But the Raspberry Pi has many pins and many outputs. So what I'd like you to do is I'd like you to add a second degree of freedom. So I'd like you have a single degree of freedom with your bicep. When you flex your bicep, it contracts the arm. When you relax your bicep, it relaxes. But in reality, that's not how your arm works. You also have triceps. So when you want to extend your arm, you contract your extensors. And when you want to flex your arm, you flex your flexors, biceps and triceps, right? So what we've done so far is a single degree of freedom. It's just the bicep. So when you flex the bicep, it contracts. And when you relax the bicep, it assumes you're flexing the tricep and it extends. So you would get that nice motion. But in reality, I'd like you to add a second degree of freedom. For example, if you're using the biceps already, add the triceps. And then I want you to modify the Python code to detect those 2 degrees of freedom, flexion and extension. And then I want you to build an arm using a motor and a joint to implement those 2 degrees of freedom. And then submit the video with a real-time video showing that you can do the control with the flexion and the extension of the robotic arm. This may require you to add a second front end, It may require you to add a second A to D. It may require you to team up with somebody and take 2 boards or 2 Raspberry Pis and put them to work on the same project. Really, the world is your oyster. If you would like to do something other than an ARM, you would like to do control a motorized car where you can go left, right with 1 degree of freedom, like contracting and relaxing. And you can do fast, slow with the other degree of freedom. And you want to control a robotic car driving around a room with muscle flexion and extension, that's fine. If you want to use the electrooculogram instead of an EMG signal, and you want to use the eye motion in order to move a cursor around a computer screen, that's fine too. What I want to see is that you have, what is absolutely required, is that you have 2 degrees of freedom, that they be bioelectric signals, that the whole thing remain wireless, and that you have a moving component. So you have a motorized car, you have a motorized arm, you have something that is motorized. If it's the electrooculogram to move a cursor, you've motorized the mouse that's moving around your screen, or you've motorized some sort of a pointer on a trackpad. There has to be a motorized component, 2 degrees of freedom, bioelectric control, implementing the practical. It's a lot of work, and it's entirely optional, but I think you'll find it very, very rewarding if you choose to take it on. And like I said, it can be worth up to 5% extra credit. Barring that, I look forward to seeing your regular submissions showing me 1 degree of freedom control of a wireless virtual prosthesis on your computer screen, and showing me that you customize your hardware in order to optimize the acquisition and the use of that single degree of freedom bioelectric signal. And you should be able to tie that all in now. Everything that you've done there should tie in with what you've seen on the Hodgkin-Huxley, with what you've seen and modeled throughout the semester, and you should have a really good understanding now of how you build bioelectric devices to record bioelectric signals, to enable patients to control the world around them, or to interface with the patient's body to control neural activity, to do things like stop epileptic seizures, cure Parkinson's disease, or control robotic limbs in amputees. And hopefully you found all of this a very rewarding course, and I look forward to seeing your contributions to the field of bioelectricity and medicine in the years to come. Thank you.